let's see, did I get a good structure? 28 valence electrons, is that right? 2 DUS, right? It could be probably a variety of structures. I ended up with something like this. I had 2 charges. You can also do something like this. One thing I can say about when you're doing structure is keep this in mind. Your functional groups are arrangements of atoms, typical arrangements. So what you could do is, especially when you get a larger formula, you could say, okay, I have a nitrogen, an oxygen, carbon. I have some DUS there. Maybe I could just start by showing an amide. I mean, you know. So you already know collections of atoms. You don't have to put it together atom at a time. For example, if you know cyano, well, you got a C and N in your compound. You got 2 DUS, so you can just have a cyano. There's your 2 DUS, and everything else should be saturated. Anybody come up with a different functional group other than a nitrile or a nitrile oxide?
Is there ever going to be a hydroxyl group attached to a hydrogen? Is that something?
Yep.
Okay, that one works.
Well, for something like this, that would certainly work. In real life, it may not be quite stable. That'd be hydroxylamine. Yeah. Variety of structures. Main thing is, leading principle is all atoms is octets. There's some exceptions to that, but usually you want to get octet for everything. What you don't want is bonds, 5 bonds to carbon, 5 bonds to nitrogen, no octet on carbon, and atoms that should have charge and you're not showing charge. Okay? What we got here, ether and an amide. I don't know if we pointed it out, the long name for amide is carboxamide. Yeah, what's the other type of amide we know? Sulfonamide, sulfonamide. That's not shortened, that's just sulfonamide. We get those, yeah? Which one's most basic? A? How do we do? Everybody got A? Yeah, A's good. Everybody got F, right? Degrees of unsaturation, 18. I saw somebody with 17. Which one did you miss? You missed the little ring up here, cyclopropane ring. How do we do on that one? Anybody? If you have questions, shout it out. Questions?
I have a question. For a ring, just one ring, is that just 1 degree? Or do you have to count each double bond?
Well, the ring is one, and then the double bonds are others. So this ring here is total of 4 degrees of unsaturation because it's 3 pi bonds plus the ring. Number of pi electrons, 8. How'd you do?
That's 6.
Somebody said 6.
Oh, later was
Who got 8? Nobody? Why not?
I forgot about the conjugation on the ends.
Why'd you forget about that? What type of orbital is this lone pair in? What type of orbital is that lone pair in? P orbital. Electrons in P orbitals are called pi electrons. Those 2 would count. So what was your answer?
I only put 2. I just,
You only put 2?
yeah. I was just thinking about the pi bond.
Did you what?
I got the cyano, so I got 4.
Oh,
I got the double bond and the.
what do you think the bonding was up here? That's a triple bond,
Yeah, I
right?
know, I just didn't pay attention to that.
That's a triple bond. How many pi bonds?
2.
Each pi bond has how many electrons in it? 2. A bond has 2 electrons. 2 pi bonds, that's 4 electrons. You got this pi bond here, that's 6, and then you got that lone pair that's in a p orbital, that's 8. Yeah? What was tricky about that?
I guess it's one, so you have to just, like,
Which ones could you not see?
well, I guess I could see it, I just didn't like, I guess think about that there was a triple bond between.
Yeah, I didn't think about that.
What'd you think that was up there? Carbon with just 2 bonds?
I didn't think about it.
Yeah, I was just like, oh, don't look at that.
Yeah.
Okay.
My fingers work.
Diltigliptin, because there's no sp2ch, right? How we doing that one?
I have a quick question.
Question?
Well, you just moved it, but the nitrogen that we were just talking about, that we had the lone pair on,
Uh-huh. A lone pairs in a p orbital, right?
not the cyanide. Yes, sir. I thought that would be an SP2 because of
It's
the
sp2.
double- But I didn't think that had SP2.
No CH.
Oh.
Are you talking about the IR question?
Yes,
Well, this is CHs. Yeah.
Now, the NH and OH is not going to be just above 3,000. Where's theirs going to be?
It'd be more like 32, 33, 3,400. Okay, I sort of gave this range. NHOH is more like 3,400. Might be as low as 32. So I tried to say that was sp2ch range I was telling you, right? Okay, the key will be posted on the 3rd floor in Science Hall as you walk down towards the lab. There's a glass case on the left, just as you start walking down the hall. All right. Anything unexpected on the quiz?
What did you say would be posted?
3rd floor as you walk down the hall to the lab. There's a glass case on your left. Okay, acid-base chemistry. We do have a handout today. It's our next outline after we finish acid-base. I'm going to, just one stack, okay? Please pass it all the way around. Acid-base. I'll do solubility. In that physical properties, there's one of the last sheets is this thing here, but it's black and white. Let's look at that also. Physical properties. On the front of the last sheet, the physical properties, but it's black and white. Here's colored, okay? Here's a compound up here. What is R? No R on the periodic table, that's just carbon. Okay, it can be 1 carbon, 2, 3, 10. R has to be defined somewhere. Now this illustrates the principle. Now first off, we have cyclohexane and water. What's going to mix? No, cyclohexane is just a plain hydrocarbon, not soluble in water. It's like oil, it floats on water. Okay, so that's dense. 2 layers. Well, this is important. If you put a compound, if you dissolve a compound in those layers, or if you just add like sugar, okay, and shake it up. First off, it'll either dissolve or it won't. If it won't dissolve, well, you're not really, you can't do this. But typically it will dissolve in one of those layers. It'll either like the water or it'll like the cyclohexane. Okay? But depending on the polarity of the compound you put in there, it's going to like one versus the other. The more polar the compound, the more it's going to like the water layer. Well, this compound, these are yellow, no matter what that R, or what that R group is. Now, if the R group is methyl, it's called methyl red. It's actually red as a solid, but when you dissolve it, it's yellow. When the R groups are methyl, so when there's 2 methyls, and you put it in here and you shake it up, that's called partitioning it. Most of the compound stays in the water, seen by the color. If you change the R groups to 2 ethyls, you start getting more in the organic layer. If you change them to propyls, it's like all in the organic layer. Why this trend? Because we're putting more of this bland hydrocarbon onto the molecule.
And that's making it more prone to be soluble in the bland hydrocarbon, the nonpolar hydrocarbon. It's actually a very pronounced effect. You might not expect there to be much difference in these two, but it actually is in this particular case.
The colored thing is the molecule on top.
That's the molecule on top, and it's causing the color. Yeah.
And would this ever cause the water and cyclohexane to mix as well? Because they're having one polar end and non-polar end bringing,
That's potentially a good question, but
not quite.
yeah, this is probably a little bit of your solute. Maybe if you added tons and tons of solute, you could get them to come together like a soap does. But typically when you do this partitioning or extraction, you don't get that concentrated.
So for the middle one, part of that is dissolved, there's still a distinct layer between.
It looks like maybe 90% is actually in that layer, and then some is just stayed in the water as it partitioned. Okay? But then when you got over here, the water was like, okay, I don't like you anymore. Go over there. The molecule didn't like the water anymore. I'm going over here. Okay. So acid base. Let's see where we left off at. We will do this type of thing today with acid-base extraction. And we'll have two layers, and we'll say which layer does the compound want to go in. So we'll be doing some acid-base chemistry. Okay, your acid-base mechanism, hybridization effect. Alkaloids, natural products, natural compounds that contain basic nitrogens, lots of nice compounds, LSD, okay, things like this, morphine. Heroin's actually synthetic. Nicotine's an alkaloid. Okay. I think we can start here. Any acid-base questions? Predicting equilibrium. How do you do that? Well, first off, you need to know reaction will favor the side with the weaker acid. What is the favored side? Hopefully you may have learned this in some other course. For example, if we react this carbanion with water, we'll get an acid-base reaction. The carbanion, the carbon, is water, right? The carbon is our acid-base mechanism, okay? We'll take an H, take, not accept. These electrons move on to here, yeah? What do we get? We get a fourth bond to H, that's methane, and then what are we producing right there? Hydroxide, so it's all there, standard acid-base reaction. All right, now I'm giving you pKa's. pK of water is 16, pK of methane is greater than 40. It's one thing you have to know. What's the acid on this side? Okay, it's a very simple question. Over here, what's the acid? This guy or the water? Water, because it contains the H that's being exchanged. That's the acid, and so it would have a pKa 16. What's the acid on this side? What has the H now? That thing has the H now, so it's the acid in this, okay? Of your two acids, which one's most acidic? Well, I gave you pKa's.
Water.
Lower pKa. You should be able to determine that anyway. Okay? Would you rather make an O minus or a C minus? O minus, okay? This is going to be more acidic. Which side's favored? The side with the weakest acid. Which side is that? To the right. How much is it favored? It's favored by the difference in your pKa's. What's the difference between 16 and 40? The difference of 24. Okay? That side's favored by 10 to the 24, at least, depending on what that greater sign means. What's 10 to the 24? That's 100 gazillion, okay? It's a big number. That reaction is highly favored.
So in this case, could we also just draw like a one-directional arrow? Since the difference is so...
Moving forward, when something's highly favored like this, I'll usually just draw a one-direction arrow. And many times I'll just draw one. And in many times it's actually in equilibrium, but one side's so favored we don't even talk about it going the other way. Okay? It would look like this.
or even smaller. Questions?
So is this from the Ka calculation that we determined that the reaction is favored the side with the weakest acid, or is that just in this? Where is that statement coming from? Reaction will favor the side with the weakest acid.
I have to think about it. It may just be something inherent. I don't know if it's actually in numbers. Okay, but basically, which is favored? Oh, which carbanion is more favored, C minus or O minus? O minus. That's more favored than that. It's another way to look at it. Maybe it was not in your just Ka calculation, but it seemed like it should have been. But it's just intuitively, you should know that, hey, if you put this in water, hydroxide is going to be more favored than this. And that's not just going to sit there. Okay, so there's some intuition there. We can keep asking. Down here, which side's favored?
Yeah.
Yeah.
What's going on here? Which is the acid on this over here? On this starting reagent, which is the acid? This is the acid, see? Because it lost the H, it gave up the H. So water in this reaction is what? Not an acid, but a base. Here's a base. Here, these electrons take the H and leave those behind, leaving a lone pair behind. The water took the H. So here, water acted as a base. Well, the acid has a pKa, and carboxylic acid is about 5. You should know that. Water 16. We don't have water up here. Water's not acting as an acid, so there's no water 16 up there. The pKa of hydronium ion is less than 0. Okay? Which side's favored, 5 or 0? 5. So here, this side's favored. So if you put acetic acid in water, it does not completely ionize. In fact, most of it sits like this. In fact, it's 10 to the 5, right? 10 to the 5 is a number we can say. What is 10 to the 5? That's 100,000? At equilibrium, you have 100,000 of these, and only one is ionized. Okay? That's a weak acid. Only 1 out of 100,000 is ionized. All right, let's do some examples here. First off, we've got to show the products. We're doing acid-base chemistry. That's the title of this handout. But also keep this in mind. As we move forward, organic 2, advanced organic, always consider acid-base chemistry first. Very quick, going to happen. Okay, before you consider any of your other reactions that we haven't even talked about yet. Acid-base chemistry. Now I gave you a pKa here. That kind of tells you that this is probably the what? Probably the acid, because pKa describes acid. Also, you know hydroxide. I know you learned that in Gen Chem. That's a base. That's okay, so show the product. I'd recommend using your acid-base mechanism. What I showed on the first pages. That's your blueprint to success. As opposed to just pulling some structures out of the air. Show it with the arrows. Show what you want to. Show the chemistry that's going to take place in the resulting movement of your arrows. What does the base do? Does it accept something or does it take something? What's it going to take? It takes the acidic H. Where's the acidic H at? Is it this one on the carbon here?
The nitrogen.
Which is more acidic? You always want to take the most acidic. The CH or the NH? We talked about which is more acidic. Okay. Would you rather make a C minus or an N minus? N minus. Yeah, that's the most acidic H. Usually it's on heteroatoms, and since you show H's on heteroatoms, usually the acidic H's are shown. What happens here? The base does what? Makes bond to H. What happens to these two electrons? They move on to that. Now there's one lone pair there.
When that moves on to the nitrogen, how many will be there? 2. So we'll still have all this. But how many lone pairs there? 2. Is there an H there? No, the base took it. But guess what? That's not a standard nitrogen, is it? It doesn't have a charge. What's the charge? Negative, because when you lose an H plus, or essentially lost H plus, that's a negative. Okay, that nitrogen owns 2, 4, 6. It's only supposed to own 5. What else did we form here?
Water.
I had OH. It had 3 lone pairs, but 1 lone pair did what? Bonded to the H. And lo and behold, what do you call that? Water. It's neutral. Because if you look at the very last sheet where I tell you some things, and you said this, you gotta have charge balance. What's the net charge on this side? Neutral and minus for a net of -1. You gotta have -1 over here, you see? You can't have 1 minus and all of a sudden have 2 minuses over there. There's charge balance. There you go. pK of the acid over here is 8. What's the acid on this side? That is it. Okay, what has the H now? That's got the H now. Now what's pK of that, Scott? 16. Which side's favored, 8 or 16? What did it say? The weaker acid. Which is the weaker acid, 8 or 16? 16. Right? Higher pKa, weaker acid, right? Okay? This is favored by how much? It's favored by 10 to the 8, which is what? What's that, 100 million? At equilibrium, you got 100 million of these nitrogen anions. Only one of them didn't get deprotonated. What does deprotonated mean? We call it H, also a proton. We deprotonate it, we remove the proton. Only 1 out of 100 billion is not deprotonated. One question we could ask is hydroxide strong enough to remove this H?
Yes.
Yeah, it's going to remove 100 billion out of 100.
So,
Question?
with all those mechanisms that are going on, if a hydroxide is more, or oxygen is more electronegative and would rather have a negative charge on it than a nitrogen would, why would the hydrogen be more likely to come over to that oxygen instead?
Okay, well this implies, which is more stable, O minus or N minus? Which is, the fact that this side is favored implies that this is more stable.
But typically O minus would be more favored.
Yeah, but why is this actually more stable?
So other stuff.
Starts with an R. Resonance. You see, what is one of these lone pairs doing?
Conjugating.
It's conjugating with not one adjacent pair, but with 2. The fact that this side's favored implies this is more stable. It's more stable because it's conjugated,
Okay.
and doubly conjugated.
Does that mean the charge is spread out more, so it's not?
Yeah, you can draw resonance structures, and some of this charge is actually on each oxygen.
So it's not like a full minus charge on the end versus there's a full charge on the on the.
Full charge on oxygen. This charge is actually spread out. You
So
can
it's
draw
not
resonance
like
structures.
concentrated.
Some of these oxygens take on some of this charge, do resonance. In fact, didn't we show that same structure when we talked about resonance back over here? Same structure. I told you why this was more acidic. Talked about that resonance over there. Not taking time to show all the resonance structures. We'll do that in due time. You can look on your own. Okay. Okay. Product of the reaction below. Next reaction. Anybody got any questions about it? Which one's the acid? Is it Daniel? No. Joe. Joseph. Joe.
On the left.
Why do you say this one?
Stronger acid.
Okay, is this an acid? So if this is the acid, then what is this?
And that's the stronger acid.
Do what?
Isn't the one on the right the stronger acid?
Stronger acid? It's got a higher pKa, lower pKa, stronger acid. That may actually work, Joe. Basically, let's pretend these numbers weren't here. And let's pretend it was one molecule. Let's pretend it was just attached there. Okay? Basically, where's the most acidic H on the board here? Over here, I mean, all you got is CH's. Is it CH or OH? Would you rather this be an acid and this become carbon minus or O minus? Yeah, okay? That's the most acidic. It's a phenol. It's very resin stabilized. You got these withdrawing. These are called nitro groups. We'll learn those in organic 2. This is actually the base. Okay? Since this is the base, we know that these electrons are going to do what? Take that H, these stay behind. What do you get? So show the result. Complete Lewis structure for the resulting other side. Show everything. Well, I just showed you the mechanism, right? It takes the H, these stay behind, and there's nothing to it. All this is the same. We got 3 nitro groups. An option had 2 lone pairs. How many does it have now? 3. And what charge is that? Minus. And what did we make? Nitrogen, it had 3 ethyl groups. What's now bonded to the nitrogen? H. Anything else we need to show here? Positive, right? It's positive nitrogen, right? It owns 4 electrons in that situation. Of course, that side is neutral, so this side better be net neutral. You can't just make a minus from two neutrals. There you go. It's just acid-base reaction. Same old mechanism. That will always be the mechanism. Which side's favored? This is the acid over here. What's the acid over there? What has the H over there? This guy. What's the pKa of that guy? pKa is 10. Okay? Told you that right there. See, this acted as a base. pKa's describe acids. That pKa is describing the conjugate acid. Where's the conjugate acid of this at? Over there. Okay? See, in organic chemistry, we don't use pKb's. In organic chemistry with bases, we use pKa's, but the pKa describes what? Not the base, but the conjugate acid. Okay? This is pKa of conjugate acid. We don't use pKa's in organic chemistry. Organic chemistry is too simple. All right? So which side's favored, 1 or 10? 10. This side's favored by how much? 10 to the 9. What's that, 1 billion? Okay. Question. Is triethylamine strong enough to deprotonate this phenol? Yes. Okay. Now most phenols have a pKa of about 10. This one is much more acidic because of these three nitro groups. Okay, don't think all phenols are going to be 1. Most are 10. Look at the table in your workbook.
So can you look at this without knowing the pKa's and determine which, or make an educated guess as to which side would be favored? Or-
You can certainly draw the acid-base product. You got to know pKa's. I mean, I make an educated guess, but I know pKa's. So ultimately, you got to know pKa's. I mean, okay, show the products down below. When I say comment on this, well, I just commented. It's the same thing I commented on up there. Okay? Comment on this right here. Show the products and say which side's favored. See, this is actually phenol without the nitros. So which one's the acid?
Phenol.
And actually, what you said earlier, Joe, didn't work here. Because up there he said this is more acidic, so that's the acid. Down here, PKF5 looks like it's more acidic.
It doesn't have the age or.
But see, that's, okay, in the end, what you want to look at is, okay, pretend this is just one molecule. And the question is, which H of the molecule is most acidic? I mean, you got CHs and CHs, and you got this OH. Would you rather make a minus on a C or an O? O. Not only would it be a minus on an O, it would also be conjugated because there's P orbital next door. Okay? So even if you didn't have pKa's, you should say that's going to be the acid. And if that's the acid, what is this? That's the base. And what do bases do? Take the H, that bond stays behind, show the result. That's pyridine. It's a benzene ring with a nitrogen. You'll find it in like vitamin B1 and 2 and 6. Pyridine rings. Look them up. So what's bonded to this H now? I mean to this N. H. What's the charge of that N? Positive. Got enough to do a charge. Recognize charge. Is that a standard nitrogen? No. Like I said, it's probably going to have a charge then. Okay, what do we get over here? That oxygen had 2 lone pairs. How many has it got now? 3. And that's a minus charge. There you go. Which side's favored? What's the acid? What's the pK of the acid over here? Which one's the acid? The one that has the H. What's the pK of the acid? 10. What's the acid over here? This has got the H. It's the acid. What's its pKa? 5. Because that's what that means. If we give a pK of a base, pKa refers to the conjugate acid. Which side's favored, 10 or 5? 10. This is favored. By how much? 10 to the 5. Question. Is pyridine strong enough to deprotonate that molecule? Is it going to deprotonate it and go... I mean, it'll deprotonate 1 out of every 100,000. Does that sound like it's strong enough? It sounds like that's a lousy job. No, pyridine is not strong enough to deprotonate that. And so actually this side, it's not going to, the equilibrium is going to lie way over here with no proton exchange. Okay, one below. It's got a hole punched out. That's just an NH2. This is an amino acid. Okay, you'll see these in biochem. Building blocks are all your proteins. These undergo an internal acid-base reaction. Basically, at this point, you can just pretend that these are not connected. Maybe we can separate it in two different molecules, but it's R. In the end, every one of these has an acid and a base. Acid and a base, acid and a base. Here we have an acid and a base. Where's the acid at? What's the name of this functional group? Carboxylic acid. Okay? What's the name of this one? Amine. And that's the alpha position, alpha amino acid. Okay? That's more acidic because you'd rather have a minus on an O than an N. And that would be resonance stabilized. It's more acidic than this. Here's your acid. Where's your base? How do we say to judge bases? They're either anions or what? Neutral nitrogens. sp3, sp2 especially. Do we have a there's no anion. Do you have a neutral nitrogen? Yeah, right there. sp3 nitrogen. There's your base, there's your acid. Okay? pKa of the acid here is 5. That's carboxylic acid. We'll talk about the other pKa, but first show your acid-base reaction. What's the product going to look like when the internal acid-base reaction takes place? Show what it'll look like. Now, if you're doing mechanistic arrow, that's great. Problem is, the mechanism arrow may not be internal. It may be where you have two different molecules, and the base of one molecule takes the H of another. Okay, and it all happens like that. The base of one takes the H of another. But basically, that's your reaction. So this takes the H, so when you draw that, how's it going to be? Not 2 H's on it, but 3. And that's R. Now how do we want to draw this over here? It acted as an acid. We showed that kind of right here. 2 lone pairs originally. Now how many? 3, that's a minus. And that's a plus. Okay? There's how it's going to exist when the acid-base reaction takes place. All your amines have taken on an H, they've taken one, and all your carboxylic acids have given up the H, they've all acted as acids to the base. Now which side's favored? Over here, this is the acid, it's 5. What's the pK? This is the acid over here, what's its pKa? This is very similar to that guy. It's about 10. The pKa of an sp3 nitrogen is about 10. Okay? Which side's favored? 5 or 10? 10. Okay? You see, this is a favored side. And this is the take-home. Amino acids exist as the two charged, dicharged. Okay? Especially at standard neutral pH. Okay? This is how they usually exist. Now, in the textbook, you'll see them drawn like this. Okay? But that's how they exist. In neutral pH. We will do some where the pH changes and it will exist in different forms. When it has two charges, anybody know what it's called? It starts with a Z, W. A what? I never heard it pronounced that way. But that's it. What do you say? You said zwitterion. You're right. I call it zwitterion. I never heard it pronounced that way. Zwitterion. Okay? Y'all look it up. Basically, it's a molecule that has two charges, and it's net neutral, plus and minus. That's how amino acids exist at neutral pH. What about pH? How will an acid base primarily exist at a certain pH? Here we're going to change the pH. This can all come from the Henderson-Hasselbalch equation, and when I took biochem, we derived that from all your pKa stuff down to a nice little equation that looks like this. pH equals pKa plus log of the base over A. Basic species, acidic species. Well, we're not going to derive that equation here. We're basically just going to learn how to use the Henderson-Hasselbalch principle to predict what we want to predict. Here's a summary. If pH is greater than pKa, B will predominate. B is the basic species. Let's see, if pH is greater, a greater pH means the pH is higher. What does high pH imply? Is that basic or acidic? Yeah, you see, when the pH is sort of on the basic side of the pKa, the basic species predominates. Now, if the pH is less than pKa, less means it implies it's lower. Now, you've got a lower pH, what does that imply? Acid. And indeed, if the pH is lower than the pKa, the acidic species will predominate. Well, what is the basic species? What is the acidic species? We go back over here and look at one of our reactions. We show both species. We're talking about a conjugate acid-base pair. For example, here and here. Do I agree this is an acid-base pair? Conjugate acid-base pair? Okay, which one is the acidic species? Left or right? Here's a big hint. The acidic species is the one with the H. Which one's the acidic species? Okay, this is your acid acidic species, and this is that's your basic species. The acidic species has the H. Okay? Please don't think the basic species has a minus. I did not say that. This example, it had a minus. Other examples, it may be neutral. What is always the case is the basic species does not have the H anymore. Now you can look through this and see how we got to that summary from just this stuff here. Because if you do a log, you can see how that'll make. Let me ask you this, those who are like math. If the basic species and the acidic species is equal, what will this term equal? 0. I'd think about it. I don't do that. So if that's 0, what are you left with? pH equals pKa. See, when the pH equals pKa, what's the ratio of your species? They're equal. But if it starts adjusting, we get what I summarized. Okay, here we go. Y'all ready to do this? Here's acetic acid. It has how will it exist at pH of 7, which is blood pH? How will it exist? Will it be in the acidic species, in acidic form, or basic form? What do we need to know other than pH? pKa. What's the pKa of acetic acid? It's 5. Okay. 5 is the thing that can vary. 7 never varies for this structure. The thing that can vary, is it on the low side or the high side of the thing that cannot vary? Is that on the low side or high side of the constant? It's the low side. And from the low side, is the acidic species going to predominate or the basic species? The low side is low pH. I'm sorry, see, I'm doing the mistake that you guys always make. I call that the constant. Now, this is the constant. I'm sorry. pKa is a constant. I'm sorry. See, that's the same mistake y'all always make. So I just made it for you. What I just did, don't do it. This never changes for the structure. pH is what can change. I can say pH of 2 or 7 or 14. I can give you any number. I can't give you but one number for that. Okay? The thing that can change is it on the high side or the low side of the constant? It's on the high side. So is the basic species going to predominate or the acidic species? High pH compared to that is basic. Basic species will predominate. So how will acetic acid exist in the blood? Will it be this or will it be this? It'll be like that. It'll be an ion. Predominantly. Not totally. What's the ratio of these two in the blood at pH of 7? It's a difference in your two numbers. 2. This species will predominate by 10 to the 2, which is what? 100? Okay? If you have acetic acid in your blood, 100 of the molecules will exist like this, and only one will be like this. Why do we learn this? So you know how molecules exist in the body. Now, if it's an ion in the blood, it's going to have different properties than if it's neutral. Some slightly different properties. For example, diffusion through a lipophilic cell membrane. You learn about it in biology, in cell, right? A polar compound like this ion is going to have a tough time going through a cell membrane. Okay. The thing below is just a miscellaneous note. There's additional miscellaneous notes on the back page. I mean, this is just pretty straightforward. Here's codeine. If you ever take codeine, you probably take codeine hydrochloride. Look at the little insert for the prescription. Okay. How do you make codeine hydrochloride? You take codeine, you react it with hydrochloric acid. Well, we know that's a strong acid. You might say it's going to fully react. But we can use our numbers. These are your two. This is an acid-base reaction. Which one's the acid? Obviously HCl. pKa is like -5, -7 or something. Okay? We get this. What's the acid here? Is it this or Cl minus?
No,
Cl minus is not an acid. It doesn't have an H. Which species has the H now? This thing has the H. What's the pK of this? That's an sp3 nitrogen. What's pK of an sp3 nitrogen?
About 10. Around 10.
Yeah, about 10. Which side's favored? -5 or 10? 10. The weaker acid. By how much? 10 to the 15. That's 100 gazillion at least. Okay, that's a huge number. All right, you see, you react codeine with HCl, it's going to completely form this. That's kind of intuitive though, because HCl is a strong acid. It's going, okay? This can actually be isolated because amines are basic enough to form stable salts. Okay? Isolate it and then put it in a pill and give it to a patient. Codeine hydrochloride. Why are most drugs given as salts? Because now they're ionic, and this is going to be more soluble in water, like in the stomach, than the non-charged compound. We can increase the water solubility by making it ionic. That's why 95% of drugs are given as salts. You want it to dissolve in the stomach, right? Actually, some drugs you don't want to dissolve. Okay? Maybe you have, you want it to do something in the stomach. So if you didn't want it to dissolve, maybe you wouldn't give it as a salt. Okay? So drug design, pharmacology. How do you want the drug to behave? Okay, there's a question to work on the back. Plenty of miscellaneous points to remind. Remember, most of these I've said.
Questions about acid-base chemistry? Very important. Acid-base chemistry will be used in, further in the course, it will be used in organic 2. We get to organic 2, and if you have me, I'm going to assume that you know this stuff. Or at minimum, if you forgot a little bit, you have this handout, and you constantly refer back to it along the way. Organic chemistry builds. We don't get over to organic 2 and I reteach you all this, or re-present it to you, right? Or when you get to biochem, Dr. Spencer's not going to sit there and re-present this. Okay? So hopefully the handout doesn't just disappear after the test, but it's a resource. Question?
That's right, you're saying, you react to pipe. Or as of,
Which compound?
yeah, coding, why would you react with the, because when you pretty high concentration, how you look at it in your stomach, why wouldn't it, you could just give it that way and it would react in the stomach and
It certainly will. But go back to that Prilosec and Nexium. They were able to get a new patent because then they made it ionic, and they said, well, even though it goes into the stomach and you say it's going to react with HCl, it still first has to dissolve to react. Because most all reactions are from solutions. And if it goes in there as a pill and just sits, that HCl may eat at it, but if it's an ionic, it'll be just more willing to just dissociate into ions and dissolve. And so that pill won't sit there for 2 hours. Quicker onset of action. And maybe you get a new patent because you think it's better than the old one and now you make more money.
can you change one little thing on even though it's the same thing when you patent?
It's a good question that the lawyers probably dealt with. And some other company probably said, hey, all they did was do this. And you know, a lot of times patents go to a judge and the judge has to make a decision.
Because you don't have to look after it's the exact same thing, after it's.
Like you're saying.
It's inside the body.
That's why if you want to go to law school, a big thing in law is lawyers that know science. And then maybe you're a patent lawyer for a drug company and you know these things and you can make an argument to the judge and you can say, hey. So drug companies want lawyers who know science. So they can help them make that money. Yeah? Okay, let's take a quick 4-minute break. Next handout is, you'll be looking at the warm-up questions. We'll move on to alkanes. I gave you the outline today. Yesterday I gave you the packet. That exception the original has to be like see, this is already.
Yeah, there are.
Put another material in here.
It was in the book, I read it, but it didn't give you the.
Here's the 2 fields. This option has 2 long pairs. instead of a hybrid, if you put another one in the P orbital, how's that new P orbital going to be oriented? The new P orbital will have to be like this. And if this lone pair is in a P orbital like this, what's the you can't do it, because this one's doing it. So there's no, if this one had two P orbitals, what to do it? It's not, that's
About the band, it's like over around the bass in the back. Well, that's just like.
what it makes us solve. Drug has to be an acid or base. Is this an acid? It's either an acid. What's an acid? NIN. It's not basic. So this is not going to react to acid. But, this be an acid. Alcohol, well, it can't be acidic. Or phenol, if it's very acidic. It's not acid or base. Can't do it.
Reaction products that take personal to use
Why did I?
Okay, guys. Let's try to get started. We have right set, says alkanes, cycloalkanes warm up. I'm going to give you a blue sheet today. Okay, we've covered a lot of the foundation. A lot of the foundation. What have we covered? A lot of structures, bonding, formulas, basic structure stuff, hybridization, physical properties, intermolecular forces, and then acid-base chemistry. All right. We're now going to move into sort of looking at functional groups. And the first we will do is mainly alkanes, simple hydrocarbons, including cycloalkanes. And then that'll pretty much, after we cover that, it'll be the test. Test 2, we move on to alkenes, compounds with carbon-carbon double bonds, and alkynes. Test 3, we come back as a little miscellaneous with alkyl halides and stuff like that. Mainly organic 1, alkanes and alkenes and alkynes. When we move to organic 2, we then cover all the other functional groups. Carboxylic acids, ethers, including aromatic rings, amides, ketones. Okay? So really fun. Now during test 2, we'll do stereochemistry. This dashed in bold stuff. Stereoisomers. Really, the stereochemistry and the stuff we're about to do is still very foundational. Okay, still going to be heavily used, and you got to know it moving into organic 2. But it's not quite as foundational as structure and formula and acid base. Okay, alkanes.
Got an outline here, conformers, Newman projections. Let's see where we're at. Got some warm-ups here. Ultram, drug. We have things, constitutional isomers versus stereoisomers. We've already defined constitutional isomers. We'll further define stereoisomers here. And then we'll do a lot more of that during test 2. Primary carbons, we'll identify, you kind of already know what a primary nitrogen is. What is that? Primary amine. The nitrogen is bonded to 1 carbon. Secondary amine, the nitrogen is bonded to 2 carbons. Same thing with carbons. A primary carbon is bonded to how many other carbons? 1, okay? So we'll see that. We'll do nomenclature. IUPAC, that's the nomenclature committee. You don't get nomenclature right, they'll knock on your door. Conformations, okay? Remember how I rotated that bond? We'll do rotations. And what's the best rotation? Alkanes can rotate. Alkenes can. Okay? And with conformations, we'll draw Newman projections. Remember Newman? Newman was actually a scientist at Ohio State. Chemist. I used to work with someone who worked with Newman. Newman was real old. He died in like the 80s, late 80s. Okay, let's do nomenclature. Let's start naming some of these. Alkanes. New nomenclature, the first thing you want to do is identify the longest chain. That's going to be called the parent. And then after each of these, it's kind of like, well, like for example, what if there's a choice? There's a choice, you're going to go with most subs. You'll see examples of this. After you identify the longest continuous chain, the remaining subs or substituents are named as alkyl groups or halogens. We'll see examples of this. All right, here's one word for you. This compound here is just a hydrocarbon. CH is all saturated. The longest continuous chain is what I circled. For example, that's potentially a chain, a straight chain. 1, 2, 3, 4. Is that the longest possible in the molecule that you can come up with? No. 1, 2, 3, 4, 5. Could I come up with any longer? Yes. 1, 2, 3, 4, 5, 6. Do you see a straight chain longer than 6? Do you see any other 6? No. It's only 1 6, and that thus is the parent. All right? So, now that we know it's 6, we have a prefix. Your prefixes are on the previous page. And what's the prefix for 6? Hex. Okay? Meth, eth, pro, but on down. You need to know prefixes up to 10. Okay? How many years in a decade? How many carbons in a decade? Okay? Now, if it's just a complete molecule, it ends in ane. Like methane is CH4. Ethane is, okay, these are condensed formulas. All these are straight chains. If it's a fragment, it ends with YL. Or when we say fragment, it'll be a substituent. If a butane is a substituent, it'll be called a butyl. B-U-T-Y-L. Butyl, pentyl, hexyl. Okay? Methyl. We'll see examples of these. So the longest continuous chain is 6. What do you want to call the parent? Hexane. So what I circled is hexane. But this compound is more than hexane. It's got something on it. It's got a 1 carbon there. That's a CH3, right? What do you want to call a 1 carbon substituent? It's 1 carbon, so what's the prefix? That's not methane, because methane is a complete CH4. This is a CH3 1 carbon substituent. So it's methyl. So this is a hexane with a methyl. Well, we got to say where the methyl's at. So you have to number your longest continuous chain. The N is number 1. But which N? What does it say?
So the lowest possible number.
3, give subs lowest possible numbers when numbering the parent. If we started at the end, you start at the end, you started here, the sub would be where? 4. Can we do better than 4? You start over here, the sub would be 3. That's going to be it, because you get your subs lowest possible numbers. The name of this compound is 3-methylhexane.
So the methyl and the alkyl is only one for the anes, the alkanes? There'll be a different one, I'm presuming, for like alkenes group, something like
If it contained an alkene, it would be a different name. We're naming alkanes. That is an alkane compound. If it has any other functional group, the other functional groups would take priority and would be named according to that functional group. Okay? So we're not going to have any other functional groups here, because we're only naming alkanes. All right. So what is this compound over here? I'm going to give you a name. This is 2-methylhexane. And hopefully that makes sense. So why is it 2-methyl? What's the longest continuous chain? 1, 2, 3? No. 1, 2, 3, 4, 5, 6. And I circled hexane. What's on the hexane? Something on there. And that's a 1 carbon, so that's a methyl. I abbreviate my methyls as ME. You'll see an ME on something, okay? Some books don't do that. Many do, I do. So this is a hexane with a methyl on it. What position is the methyl at? Well, you can number your chain 1 to 6. And the methyl's at the 2 position, right? 2-methylhexane. If you're thinking that you wanted that to be the longest chain, then I'm going to erase it. Probably don't do it on your paper. What if I made that the longest chain? It's also 6. And what would the name of this be? It's still 2-methylhexane. Okay? What's the relationship between 3-methylhexane and 2-methylhexane?
Constitutional.
What type of they're isomers, they have the same formula. What's the formula of this compound? Real quick. 6 plus 1 is 7. C7, H1. 16. It's saturated, so it's 2N plus 2. You can show all your 16 H's there if you want. They both have that same formula, so isomers. What type of isomers? Forget you? Constitutional. Why?
Because it has the same formula but different structure.
Different connectivity. Because that one, the methyl's connected at the 3 position. This one, the methyl's connected at the 2 position. Same formula, different connectivity. All right, here's a hint. Don't tell anybody I told you this. All right. Constitutional isomers will have different names. It's a different name, right? It's 3-methyl, it's 2-methyl. Here's another. Stereoisomers will have the same name. Stereoisomers will just have to put some type of descriptor in front of the name. All right. Name this compound here. Do it on your paper. Take a little time. Do it on your paper. Longest continuous chain, Lauren? 7, let's see. 1, 2, 3, 4, 5, 6.
I think we're
Well,
going
we're
to.
gonna-
1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6, 7. Ah, right through there. Happens to be just right through there. Straight. What's that, 7? Is there another 7 anywhere? 1, 2, 3, 4, 5, 6. 1, 2, 3, 4. 1, 2, 3, 4, 5, 6. I don't see another 7, no? Okay, so what's the parent? Heptane. But our heptane has something on it. What is this guy? A methyl? What is this guy?
For ethyl.
That's an ethyl, ET. Okay? Methyl and an ethyl. What's the one position of your heptane? It's either the left or right. If we're over here, that's 1, 2, subs are at the 3 and 4. 3 and 4. If this is the one, subs are at the 1, 2, 3, 4, and 5. Which is better, 3 and 4 or 4 and 5? So you want this side to be 1. Now when you list your subs, you just list them in alphabetical order. Okay? And I see that this is wrong. I don't know, when I added this, I must have been distracted or something. I added it last time, and I remember it was wrong, I didn't remove it. According to alphabet. So what do we want to list first? E or M? 4 ethyl, 3 methyl heptane. And that's all one word. There's no dash between methyl and heptane, there's no space. Okay, E comes before M. We're not listing according to numbers. Hello, right? Everybody agree we have a heptane that has an ethyl at the 4 and a methyl at the 3? Okay, let's name this one down here. Longest continuous chain. Let's do it here real quick. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6. I see an 8. Is there another 8? Is there anything greater than 8? Okay, 8 would be what? Octane. What's on our octane? I got a methyl there, and ethyl here. What's the one position, left or right? 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Oh, either way we go, it's 4, 5. But hold on. How are we going to list this? There's 2 methyls. There's 3 subs. There's 3 subs, really. If we come this way, it's 4, 5, and 2 subs are at the 4. If we come this way, it's 4, 5, but the 2 subs are not at the 4, but at the 5. Would you rather have the 2 subs at the 4 or the 5? No, alphabetical is not until you list it. Numbering is subs lowest numbers. Here. You got 3 subs. After we list it, you'll see what I'm talking about a little bit. Okay, what's the name of this guy? 5 ethyl.
4, 4 dimethyl.
4, 4 dimethyl octane.
So both of those things from 3 are then wrong?
Both for what's wrong?
Or is it die, actually? It says part 3 gives subs lowest possible number when numbering parent, if choice go alphabetical.
we listed in alphabetical, E and M. Mono, di, tri, tetra, that doesn't count in alphabetical.
Let's say it's the, okay. So 2 all twos.
E and M, we listed the alphabet first.
So if you go 3 with a number and take precedence, or there's no possibility of that? 2 always take precedence over
What's the conflict?
You said whenever there's 2, that'll always take preference for number.
Whenever there's two what?
2 groups on one of the.
No, we gave subclosed numbers. Subclosed numbers. If this is 1, we get a 4, 4, 5. If this was 1, what would it be?
5, 4, 4, 5, 5.
It'd be 4, 5, 5, which is better, 4, 5, 5 or 4, 4, 5? This is better, subclosed numbers, 4, 4, 5. That's why I named it as 4, 4, 5, and this is the one end. Subclosed numbers. We just had 2 methyls have to be on the same carbon. The methyls could have been on different carbons. You still could have called it dimethyl, but maybe it would ended up being a 2,4 dimethyl. You can still use dimethyl, even if it's on different carbons. But you have to say, are the 2 methyls on different carbons, 2,4, or are they on the same carbon, 4,4 or 5,5? Question?
So if you had, like if you had methyls on different numbers, you would just list the same alphabetical order, but just with the different numbers?
Yeah, you can still say dimethyl.
Okay.
Because you should not say like 6-methyl and 7-methyl. You got 2 methyls, say dimethyl, just put both numbers in front. It's either 2 different numbers or they happen to be on the same carbon.
So for that same one, if you instead of having the 2 methyls, you only had 1 methyl, then it would be 4 ethyl, 5 methyl. Octane.
Yes, because then you would use alphabetical to decide. Because if there's a choice, go alphabetical. If you got 2, 4, 5s, which is best, 4, 5 or 4, 5? If choice, go alphabetical. Then you would do alphabetical, and the E would become before the M. Complex sub. What's a complex sub? It's just nothing more. It's a sub with a sub. Okay? Those subs were methyls and ethyls. They didn't have subs on them. Complex sub is a sub with a sub. Is this it here? Longest continuous chain. 1, 2, 3, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 6, 7, 1, 2, 3, 4, 5, 6, 7, 8, 1, 2, 3, 4, 5, 6, 7, 8, 9. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8, 9. Oh, that's a 9. But I had another 9, right? 1, 2, 3, 4, 5, 6, 7, 8, 9. That's also a 9. I got 2 9s. Did anybody see a 10? What happens when we got two parents?
The one with the more groups?
What does it say up there? If choice, go with one with most subs. It's going to be A and B. How many subs on B? This guy coming off, basically it's 2 things. 2 subs. How many subs on A? Boom, 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 boom. You see? A has more subs. You get rid of that 9. A has subs. Everybody agree that that 9 has more subs? Okay, so we use that exception. There we go. Now what is on? First off, what's 9?
9.
No name. What's on here? Methyl?
What is this?
Propyl.
Propyl, usually PR, I'll write it out, propyl. What is this?
Same.
Well, that's also a propyl. But what is that?
Isopropyl.
It's a sub with a sub. Isopropyl is a common name, it's not IUPAC. Because, here we go, coming off is one carbon, 2. And we can circle this sub, I mean, just like if I circled this. This is a plain propyl. There's a plain ethyl. But the ethyl has something on it. What's on it? Methyl. So that's an ethyl with a methyl. It's a complex sub. Okay? Nothing to it. Let's first deal with this. We named this almost like we were naming before. The one position, though, by default is always the first carbon coming off your parent. That's 1, and that's 2. So that's 1 and 2 of your ethyl.
Would there be 4 coming off because of that little extra part on the left, or would you not count that?
Like, what part coming off?
That sticking out, one below, this, yeah, that part.
Oh. You mean 4 subs?
Yeah,
Yeah, it's got 4 subs. 1, 2, 3, and 4.
oh, sorry. I thought-
Those 3 are propyl, propyl, methyl. The 4th one is a complex sub. What if that was just that? That's an ethyl. What's on the ethyl? At what position? Yeah. See, this is a 1-methyl ethyl. That's what that is there. A 1-methyl ethyl. That's IUPAC. What do we also call 1-methyl ethyls, Utah?
Isopropyl.
It's also called an isopropyl. Note that there's no propyl in this here, the IUPAC. Propyl because it's 3 carbons, but it's not a straight, it's an isomer. Okay, but we'll get to that a little bit later. IUPAC right now. Okay, we got methyl, propyl, 2 propyls, and a methyl ethyl. If we list these alphabetical, okay, and we'll do it down here, what comes first? Well, we got to number the parent first. What's the 1 position?
Right there, where your finger's at.
I can tell it's going to be over here. If that's the 1 position, your first sub is not going to be until 5. Basically, it's like aces high. For example, a 110 beats a 2-3. This is best. Pretty much, your first sub won't have lowest number. It's like aces high. So I can tell that, the first sub over here is not till 5. This is going to be 1. So that's 2, 3, 4, and 5. There's no subs through there. What do you want to list first? M, methyl ethyl, or propyl? Methyl. 2-methyl. Now we're going to list the methyl ethyl. Now we list that in parentheses because it's a complex sub, just like that. We've got to say where it's at. Where is that at? It's at the 3 position. So at the 3 position of a parent, what do we have? A 1-methyl ethyl. See, at 3 position is that thing. Then we have 4 and 5, but it's the same thing, so we can do what? 4,5-dipropyl. That's all one word, okay? 4,5-dipropyl, no name. But this thing in parentheses is a complex sub. Not that complex though, okay? There are common names for some complex subs. They're listed below. If I ask you for just IUPAC, it'd be this. A common name is not IUPAC. So they are good to know. The one on the right you can name on your own. Okay, let's look below. Common name subs. The complex one we just named is actually called an isopropyl. This means it's coming off of something like the main chain. That's different from an N-propyl. N meaning normal or straight chain. N. This is an isomer of the propyl, and so it's that. Note that in the common names, there's 3 carbons, so it gets called a propyl. But in the complex name, we didn't call it a propyl. We call it a 1-methyl ethyl. There's only 2 possible for propyl. For butyl, if you draw butyl, 1, 2, 3, 4, there's actually 3 isomers. Isobutyl is like this. It's actually the branch here, but it's still 4 carbons. Secbutyl has the branch at the first carbon. So this is a secondary carbon right there. See, that's a little bit misleading. If we call this X, that's non-carbon. How many carbons is that bonded to? If that's not a carbon? 2, so it's a secondary carbon. That's why it's called sec-butyl. Okay. Up here, your first carbon, that's not carbon there. How many carbons is it bonded to? Only 1. So that's actually a primary carbon. Okay. Your sec-butyl group, the first carbon is a secondary carbon. That's why it's called sec-butyl. This is a tert-butyl. It looks like a cross. It's still 4 carbons. If that's not a carbon, how many carbons is that carbon bonded to? 3. Tertiary. And it's called a tert-butyl. I'm sorry, I'm surprised I don't have tert. But usually tert is just shortened to T. So you hear somebody say T-butyl, it really means tert-butyl, and that's that cross, where the first carbon is tertiary. Preston.
So in the one we just did, with the complex subs, if the methyl ethyl was bonded to something other than like anything other than a carbon, we would call it isopropyl.
You can, it's a common name. Common name is an alternative name. Okay? If I ask you for IUPAC, no common names allowed. Maybe I'll say you can use common names. If I say you can use it, then you could back up there. We don't have the name. We could have called this a 3-isopropyl. But if it's isopropyl, it's now not in alphabetical order. It should have been here. Because isopropyl, the I actually counts. Okay? That's IUPAC. This is common name, not IUPAC. But still, your common names are good to learn.
Are these designed to be unique? I assume it would be with the complex names. There would only be one structure that you could derive from that given common or
Yeah.
complex name.
Yeah, an IUPAC name should be unambiguous.
On the test, when you have the section for Jess, are we going to use common names, or can we use either, or if you give us the option?
Pretty much you need to know these comments, because all these comments are so common. Okay, if you're in lab and someone's talking about T-butanol, you need to know what to talk about. Okay. For sec-butanol, things like that. These two are the two that can be confused. I tried to tell you that the sec-butyl has a secondary carbon, has the first carbon. I mean, that's just a cross. There's only 1 isopropyl, so it's really not much there. Cycloalkanes. Now, these are also alkanes. Usually you call alkanes saturated hydrocarbons. It's really not a saturated hydrocarbon. Because of the ring, it's got a degree of unsaturation. Sometimes somebody may loosely say that's another type of saturated hydrocarbon. Okay? But we can certainly have these cyclobutane. You can even have cyclopropanes. There's actually a lot of drugs with cyclopropanes. I gave you a sheet. Okay? 3-membered ring. You might think it's very strange with 60-degree bond angles, but it's actually very common in drugs like Cipro. Probably the drug on the front of the workbook probably has a cyclopropane in it. Okay. So you just call these cyclo whatever. That's 4 carbons, so it's cyclobutane. This here is 6 carbons, and so what's that? That's cyclohexane, and if there's nothing on it, just cyclohexane. Sometimes used as a solvent in the lab, cyclohexane. This would be a substituted cyclohexane, and so let's name it. Well, the parent is your ring, cyclohexane. And so there's no looking for the longest chain or anything. What's on the cyclohexane? We have an ethyl, propyl, and F. How are we going to name the F? Halogens are named just fluoro, chloro, bromo, iodo. So we'll do it. Now the one position is, there's no N. The one position can be anywhere. But we want subs to have the lowest numbers. So basically we want a sub to be at the 1 position. But which one do we want to be at the 1? If this is 1, what would that be?
3.
Oh, you went this way. It'd be 3, and that would thus be 4. Can we do better than 1, 3, 4? If this is 1, that would be 2, and this would be... Okay, that's better. Can we do better than 1, 2, 4? What if this is 1, 3, 6? Or we could say 1, 2, 5. That's better. 1, 2, 5, but that's not better than 1, 2, 4. 1, 2, 4 is the best. And so I'm going to say that that's the 1 position, a number like that, and give subs those numbers. Well, there's not an N to choose from. So, alphabetical order, where comes first? Ethyl. 2 ethyl. What's next? 1 fluoro. F-L-U-O-R-O. Fluoro. Like fluorine, except instead of I-N-E, it's O. And then what else is there? 4 propyl. There's no dash between the propyl and the cyclohexane. If that's that, what is this guy over here? That's the same exact thing, except what's the difference? Except this is 1, 2, 3. Why is that the 1 position? Why not this? Because if that was 1, it'd still be 1, 2, 3. I'll let alphabetical aside. I put fluorine before propyl. Okay? What's the difference? This is the 1, 2, 3 isomer. And we can refer to that one as. Where this is the 1, 2, 4 isomer. What type of isomers are they? Constitutional, because the difference is, here the propyl is connected at the 4 position, here the propyl is connected at the 3. Different connectivity. And different names.
Professor, so for the substitution groups, do you not give preference to like non-hexanes? You see, so if you have a halide or you have a hydroxy group, do you start that as 1 or you always?
Okay, but again, we're just naming alkanes here. If it was a hydroxy group, it would be an alcohol, and we'd be naming alcohols. That's why I don't have a hydroxy group up here. Okay? Everything we're naming is alkanes. You're right. If there was no H there, we might call that the 1 position. But we're not doing, it would be that way an alcohol. We're naming alkanes. There's also different names that kind of work, and you actually have to wonder which one is really IUPAC. That's why ultimately a given compound may go by 2, 3, 4, 5 names, some of them being slang and not really officially approved.
That's why you gotta be careful. Ultimately, the best way to find a compound is to go by the chemical abstracts number, because there's only got one number, like a social security number. That's why people like firemen, they don't like to deal with names, because they go in, they see all types of names. They just want to know the chem abstract number. Okay? Every compound's just got one. That way they can look it up by the number and boom. What are these over here? What's the name of this guy, real quick? It's a cyclopentane. What's on it? A methyl and that's one, that's carbon, what's that, a butyl? 1, 2, 3. I call butyl 1, that 2. What do we got here? 1 butyl, 2 methyl cyclopentanes. Do I agree? Michelle? Well, what's this one over here?
It's a stereoisomer.
Does this have a different name?
Just got like a,
That's the same name, isn't it? Would you name that any different than we named the other one?
you'd have to have,
So what's the relationship between these two? Are these constitutional isomers? No, I told you constitutional isomers will have different names. But these are isomers, or are they? Because we have to look at, maybe they're just drawn differently. Like this. Is there any difference between this and that? Did I just show you two different hands? No, it's one hand. So we have to figure out if these are really different. Indeed, these are different. Me telling you they're different means they're isomers. What type of isomers? Good, they're stereoisomers. But then what type of stereoisomers? So stereoisomers have types. Basically, first thing here is these are not constitutional isomers, right? These differ in the projection. One of these have both groups forward, and one of these have groups back, but they're both connected at the shoulder. They just differ in their orientation in space. Okay, please look ahead. There's a miscellaneous page, miscellaneous stuff. The main thing we're going to get into is, there's more on isomers over here. Please look at that. Big thing we're going to be getting into, you need to be doing some pre-reading for tomorrow, is the sheets with the confirmations. Okay, that, energy levels, Newman confirmations, warm-up sheet, confirmation questions. We'll be doing confirmations with models tomorrow. Newman confirmation.